Welcome back to another video where we're learning about different tests for the convergence of an infinite series. Remember that a sequence is an ordered list of values separated by commas, and the infinite series is based on the sequence by taking out the commas and replacing them with plus signs. Now, we were in the beginning thinking of it as the sum of an infinite number of numbers, but we discovered with conditional convergence it's not really a good way to think about it. Instead, we need to think about the sequence of partial sums and that the infinite series converges to whatever the limit of that sequence of partial sums is. That's really what the value of the infinite series is. However, we did see that if we have a series that's absolutely convergent, when we take the absolute value of it, we saw that those did always converge to the same value when they converged. Any rearrangement of terms, even if it produced a different looking series, still converged to the same value. But we saw with the alternating harmonic series that that is not the case. And in that sense, when you have conditional convergence, you simply cannot think of an infinite series as an infinite sum because it doesn't make sense. A rearrangement of the terms produces a different looking series, which may converge to a different value. So again, it's only when we have absolute convergence that the value the infinite series converges to remains stable and does not change. This is something important to remember moving forward. So absolute convergence is the most powerful type of convergence we have. It causes that value the infinite series converges to be stable, which is, of course, what we'd like to have. We're going to now be looking at the last two tests for the convergence or divergence of an infinite series, the ratio test and the root test. Now, the root test only applies in a very narrow set of infinite series, but when it is needed, probably none other test will do. So when you need the root test, you need the root test. And we'll find that when we go into chapter 6 and we're studying power series, there will be occasions we'll need the root test. Again, used in a very narrow set of infinite series, basically the ones where the whole thing is raised to an nth power or something like the nth power. And then we apply the root test to get rid of that nth power on the whole thing. The second test that we're going to be studying is called the ratio test. Now, I'm so excited that we're here because the ratio test is my favorite test, hands down. It has a very wide application. So probably my second favorite test is probably the integral test, just because I like to integrate. But the ratio test has a very wide application. It does not require that the terms of the sequence always be non-negative. Remember, that's one of the requirements of the limit comparison test and the integral test. I know there are conditions on each one and they're all slightly different, but it is important that you memorize what the conditions to apply each test is. You cannot apply a test if the conditions don't hold, and they don't all have the same condition. So we see that the ratio test does not require strictly non-negative terms in the sequence, so it has a wider application. It does, however, have a condition, but it's a relatively small one, and the condition is that at some point, again, we're talking about the tail of the sequence, that in the tail, all the terms are never zero, so they're non-zero, not non-negative, but non-zero. They could be positive, they can be negative, but they can't be zero from some point forevermore. So it will eliminate us from using it on some series where occasionally we get zeros forevermore. In other words, we can't find a tail for which none of the terms are zero from that point on. But again, this is a relatively minor restriction, and we're going to see that the ratio test applies in the widest possible variety of places compared to all the other tests that we've learned. It also happens to be one of the easier tests to implement, and it works really well with factorials. Now, we studied factorials a little bit in the previous section, and remember, factorials are the expression with an exclamation point, So 5 factorial is 5 times 4 times 3 times 2 times 1. And we discussed how fast they grow, that they are incredibly fast growing. We're going to see that again today. And we can't use the integral test on anything with a factorial because the derivative and the antiderivative of factorial expressions is not defined. So it's impossible to use the integral test, which would be probably my second choice. We could use the limit comparison test if all the terms are positive, but if they're not all positive, then we're stuck and we would need to use the ratio test. And in fact, many students just go to the ratio test first, provided all the terms are not zero at some point on, because it has the widest application and it's one of the easiest to implement. So we're going to see that the ratio test also gets used a great deal when we're talking about power series. Remember, their whole purpose to what we're doing is trying to get to a point where we can represent transcendental functions like e to the x or natural log of x, or even the trig function, sine, cosine, with things that look like polynomials added together. In fact, they are polynomials added together. They're infinite series consisting of polynomial terms. Now, why polynomials? Well, because we like polynomials. They're easy to differentiate and easy to integrate. So we're going to have infinite series of polynomials, which will give us the value of that transcendental function, e to the x or natural log of x, under a narrow set of conditions. So that's the whole purpose of what we're trying to do. And we're going to see that the ratio test will help us narrow down over what interval we can make that approximation. So this turns out to be one of the more powerful tests that we use because it also tells us when that power series is applicable over what interval. So we're going to go ahead and start today with the ratio test first, and then the next video we'll study the root test, which again is a relatively, well, it's actually a super simple test. It's one of the easiest ones after the divergence test, but it only applies in a narrow set of places. So let's go ahead and get started with the ratio test. I'm going to share my screen with you so that you can see what I'm looking at. And I do want to make sure that today I share it in such a way that you can also see the internet when we need to, because I have plotted all of the examples onto the sequence of partial sums plotter so that we can see what the sequence value is doing, and also so that we can view the sequence of partial sums so that we have some inkling of whether or not we expect it to converge or diverge. And we'll talk about why that works. Before we get too far into it, though, we want to review what we've learned about factorials. Remember that the ratio test is ideal when you have a factorial in the sum end. So remember, the sum end is the part after the sigma. So why is it ideal? Well, you can't use the integral test because you can't take the derivative or integrate factorials. You could do the limit comparison, but that requires all the terms be non-negative. So the ratio test is one of our favorites to use in this situation. It's no more difficult than the limit comparison test, so it tends to be our favorite. So reviewing what a factorial is, remember you represent it with the exclamation point. So n factorial starts at n and multiplies by all the positive integers below n down to 1. So n times n minus 1 times n minus 2, n minus 3, n minus 4, down to 5 times 4 times 3 times 2 times 1. Now this only works for n greater than equal to 1. By definition, you'll see there's a 3-bar equal here, and a 3-bar equal is the mathematical symbol for defined by definition. In other words, it can't be proved. We just said this is so, therefore it's so. So kind of like a because I said so. So 0 factorial is defined to be the number 1. So 0 factorial can show up in the denominator of an expression because it is equal to the value of 1. Now, here are some values of factorials so that you can see how massively fast they grow. They make exponentials look like they're standing still. So remember, we have the relative growth theorem, which tells us that natural logs grow the slowest. And then algebraic functions, polynomials, the square root of x, rational functions, all of those algebraic functions grow the next fastest. Then exponentials grow the next fastest after that. And then we have factorials, which is this group, which grows faster than exponentials. Our last group we're also going to see today, they're called tower functions. And maybe I need to go ahead and write that down so that you can see it. So this is called the relative growth theorem. And it doesn't show up in all books. So I'd like to include it in my lecture notes so that students have an idea of what it is. And what it's talking about is it's talking about how rapidly these functions increase to infinity as x goes to infinity. They all do go to infinity, but faster, some of them, than others. And by faster, we mean on an order of magnitude larger, so like a larger size of infinity. I know that sounds crazy, but that's kind of what we're talking about. So we have the natural log functions here, and then we use this double less than to represent that it grows on an order of magnitude less. And then we have the algebraic functions. So that's what we're going to have next. So we have algebraic functions. So this is polynomials, roots, rational expressions. Basically anything you add, subtract, multiply, and divide the variables or raise them to a power or root. So polynomials, radicals, and rational expressions. Right? So these are the ones that we dealt with most often in college algebra. And then the next class of functions, of course, would be the exponentials. So this would be like e to the x or 2 to the x, something like that. E to the x, 2 to the x, all of these equal to y. Now we know those look like this, and they do indeed go to infinity as x goes to infinity, and in an order of magnitude larger than any algebraic function, right? And then after exponentials, we have factorials. And that's what we're looking at right here. And then after factorials, we have what are known as tower functions. And tower functions are the fastest growing class of functions that we tend to look at. So these are in factorial. And here we have a tower function, which is a variable base and a variable power. Now, it doesn't have to be x to the x. It could be x squared plus 3x minus 9 in parentheses to the 2x plus 2 power. It's just anything where you have a representation of the variable in the base and the variable in the power, right? So those are called tower functions. And in fact, you can have it built even higher. You can have another power on that and it will grow even faster. So these are the fastest growing functions. And again, we're talking about orders of magnitude of infinity, how fast they go to infinity. Now, why is this something useful to know? Well, when we take the limit as x goes to infinity, and of course, we're going to be looking at sequences, so our variable would be n. But when we look at something like e to the x over x to the 18th minus x squared plus 42, I don't actually have to apply L'Hopital's rule 18 times. I can, but I don't have to, because I know that exponentials fall further to the right in a relative growth theorem and grow on an order of magnitude larger than any algebraic. In other words, this goes to infinity so much faster, it overpowers this type of function, and it's going to pull the whole thing to infinity. So this is a way of using the relative growth theorem, right? On the other hand, if I had the reciprocal of that with the x to the 18th in the numerator and the e to the x in the denominator, that would drive it down to 0. So I can judge by the type of function how quickly it goes to infinity. And I've got different orders of magnitude of infinity, which I know that sounds crazy, but not all infinities are equal. Some are bigger than others, right? This is something you can study in topology, which is a fascinating subject, but it'll really blow your mind and make your head hurt. Fascinating subject, really fun. Let's take a look now at these factorials that you see here. One factorial is just 1. And 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial just multiplies the previous result by 4, so we get 24. 5 factorial multiplies the previous result by 24, so we get 120. Notice how rapidly this grows. And this is incredible. I mean, we think of exponentials as being really fast, right? I mean, it's exponential growth. We all make that sound like it's the fastest thing on earth. It's not, all right? These factorials are growing incredibly fast. 11 factorial. I mean, we're only at 11 factorial. We're not talking about 2022 factorial. We're talking about just 11 factorial. And we're already almost at 40 million. All right, it's going to infinity incredibly rapidly. Now, you'll notice that on all of these, that one way we can get from one to the next is simply to take the new digit and multiply by the previous result. And so this is a skill that you need to develop when you're working with factorials. In other words, you can strip out a certain number of values at the beginning, and you can think of 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 as 8 times 7 factorial. So that's what I mean by strip out a term at the beginning. I stripped out the 8 and then multiplied it by 7 factorial. But I could also strip out the 8 and the 7 and multiply that by 6 factorial. Or I could strip out the 8, the 7, and the 6 and multiply by 5 factorial. Now we can also do this with powers of n, and this is where we use it the most often in the ratio test. So if we have n factorial, I can think of it as n times, notice n minus 1 must be in parentheses. This is n minus 1, the quantity factorial. And then in front of n minus 1, I'd have n minus 2, so I can write it as n times quantity n minus 1 times quantity n minus 2 factorial. Or I could strip out 3 terms at the beginning, n times n minus 1 times n minus 2 and times n minus 3 quantity factorial. We need to be able to do this so that we can simplify when we're using the ratio test. And you can see here that we have some examples of how you can use the stripping out factors at the beginning to reduce fractions. So we're going to start with something that's just numbers instead of working with the variable n. So we're going to start with 13 factorial over 8 factorial times 3 factorial. Now, factorials also come up a great deal in probability and statistics. So combinatorics and probability, they're just all over the place in those formulas. So you see them there a lot as well. So what we do is we take the highest factorial in the numerator and the highest factorial in the denominator. We compare the relative sizes. Now 13 factorial is bigger than 8 factorial, but I can rewrite 13 factorial by stripping out the first 5 terms until I get it multiplied by 8 factorial. So I get 13 times 12 times 11 times 10 times 9, stripping out the first 5, times 8 factorial. I don't expand the 8 factorial that's in the denominator because I want to cancel these two. And then I've got a 3 factorial, which most of the time it is helpful to go ahead and write it as 3 times 2 times 1, because after I've canceled the 8 factorials, I want to reduce it. So I know, for example, that 3 times 2 is 6, and 6 goes into 12 2 times. So the result is 13 times 2 times 11 times 10 times 9, which is 25,740, right? So this is a way of using the factorials, backing the highest one down until it matches the other next highest one, and then using that to cancel those two. Now, how would you apply this if you didn't know what the number was, but you had an expression in n instead? So we have n plus 2 factorial over n minus 1 factorial. Now you have to be careful about which one is bigger. Clearly, taking an n and adding 2 to it is going to be bigger than taking n and subtracting 1. So then I need to back this down and strip out the first few terms until it matches n minus 1 factorial. So I take n plus 2 and then I pull 1 off. Remember, each time you reduce it by 1. So then it would be n plus 1, and then n by itself, and then n minus 1 factorial. So then the n minus 1 factorials cancel, and I'm left with the product of n plus 1, and n plus 2, which of course I could multiply it out. It would give me something that's cubic in n. You do need to be extremely cautious with the parentheses and very, very careful with the definitions of the factorials. You have to follow the strict order of operations. Factorials get done before multiplication. So 2n factorial without parentheses is 2 times n factorial. So the factorial only applies to the factor it's directly sitting on unless there are parentheses present. So this is kind of like the exponent rule. So we see that we have 2 times n factorial, which is just 2 times n minus 1, n minus 2, on and on and on. But if I put the 2n in parentheses, and then I put the factorial outside the parentheses, well, that's a whole different kettle of fish. 2n quantity factorial is 2n times 2n minus 1 times 2n minus 2 times 2n minus 3 times 2n minus 4, all the way down to 5 times 4 times 3 times 2 times 1. So you have to be very, very careful about parentheses and what the definitions mean. Let's now go ahead and state the ratio test. So the ratio test really only has one condition on it, that at some point in the tail of the sequence, all the terms need to be non-zero. Other than that, you can use it anytime. So you can use it when it has positive terms in the sequence. You can use it when it has negative terms in the sequence. Just at some point, you've got to be able to cut off the head and set it aside and say, from here on, no term is 0, right? So that's not really a huge disadvantage for most of what we do, because most of what we do, the sum ends aren't ever 0 from some point on. Not always the case. We're going to see when we get into power series that particularly when we're looking at trig functions, that doesn't happen. In fact, every other term may turn out to be 0. So now we're going to go ahead and state the actual ratio test. And the ratio test is really pretty straightforward. Let's see if I can get it all exactly a little more centered on the page. So now we're looking at this. It says, suppose you have some infinite series based on a sequence a sub n. We don't know anything about a sub n except that at some point the terms are not 0. So from some point on, none of the terms are 0. Then we're going to define rho again, and be sure when you write rho that you're not writing a P. It's not a P. You start at the bottom and in one motion, go around to the top. So it's not like a ball and a stick. There's no stick and no ball. It's one continuous motion. So rho, standing for ratio, R for ratio, is equal to the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. It's a little bit similar to what we saw with the limit comparison test, with a couple of exceptions. Note that in the ratio test, we're forced to take the absolute value of the expression inside the limit. That's because we don't know if the terms of a sub n are positive or negative. So in fact, we're testing for a much stronger type of convergence. The ratio test will give us absolute convergence, which is really what we want, because that means that the infinite value, or the sum, well, let's see, how can I see this? The finite value of the infinite series will be stable no matter how you rearrange the terms. Even if it leads to a different looking series, it converges to the same finite value. So absolute convergence is what we want. And it's similar to the limit comparison in that we're taking the ratio of two things, but it's different in that these come from the same sequence. These are both coming from a sub n. You're taking a sub n plus 1 and dividing it by the expression in front of it. Whereas in the limit comparison test, we were taking the unknown sequence and dividing by a known sequence. So two completely different sequences. This time, they're the same sequence, and we're dividing the later term by the one right in front of it. And we're taking the absolute value of it. Now we have three results down here that we need to discuss. The first one is if rho is between 0 and 1, including 0, but not including 1. So again, we want to include 0, but we want to leave off 1. So we have close 0 to open 1. If rho is in here, then this infinite series converges absolutely to some finite real value. And no matter how you rearrange the terms, all of the rearrangements will converge to that same value. S infinity is stable, it does not change. What's the next thing? If rho is greater than 1 or rho goes to infinity, then the infinite series diverges. All right, so the infinite series diverges, does not converge to a finite real value. In other words, the sequence of partial sums is not approaching a finite real number. What happens if we get rho equal 1, which of course connects these two? Well, then the test is inconclusive and we have to try another test, probably the integral test, maybe the limit comparison test, if the terms of the sequence are strictly non-negative. On the other hand, if they're not non-negative, then maybe we do the alternating series test. I mean, that's really what we've got in our arsenal so far. We will learn one more test, which is the root test. But in general, what we're going to find is if the ratio test gives you rho equal 1 and it's inconclusive, the root test would probably give you the same result. It would also be inconclusive. So when the ratio test fails, we don't tend to go to the root test because they tend to give the same result, right? If all the terms are positive anyway, you can drop the absolute values, you won't need them. The proof of this is pretty long and involved, and I mean, it's got the comparison test and it's got another test in it, so we're not going to go through the proof of it, but you can find it in the textbook. We're just going to apply the ratio test. So when do we use the ratio test? When is it ideal for using the ratio test? Technically, it can be used anytime, provided the tail of the sequence at some point, all the terms are non-zero. But the ratio test is really well suited for anything that has factorials in it, because we can't use the integral test on that. It's also really good when we have expressions involving exponential functions. So like e to the x or 2 to the x or 5 to the x, anything that's exponentials, or some combination of factorials and or exponentials with algebraic expressions, like n squared or n minus 1 or n squared plus n minus 5. Those are algebraic. All right, so now that we've talked about when to use the ratio test and what it is, we're going to go ahead and take a look at an example. So this is example number 1. Now, don't click on the link yet if you have my notes at home. If you don't have my notes at home, I'll leave it here long enough that you can get that copy down so you can see it, but don't click on it yet. So we want to use the ratio test to determine whether this series converges absolutely or diverges. Remember, there are 3 possible solutions with the ratio test. It converges absolutely, the most powerful type of convergence, the one we really want, or it diverges, or we don't know. We have to do a different test. So those are our 3 possibilities. So if it converges absolutely, which is fantastic. It means that the value of the infinite series is stable. All right, so we have this series from n equal 1 to infinity of 4 to the n over n squared. We're going to dive right in and we're going to do the ratio test. And we're going to talk about what we probably should have done first. All right, so we're going to do not the right thing first, and then we're going to talk about why we should have done it slightly different. So remember, the ratio test requires that at some point, all the terms in the sequence are not 0. Doesn't care if it's positive or negative, just not 0. Well, 4 to the n is always strictly positive. It's exponential, approaches the x-axis, but we're only concerned with 1 to infinity, so it's definitely always positive. And n squared, providing you start at n equal 1, is also going to be non-zero. So we have a non-zero divided by a non-zero, so they're always non-zero. In fact, they're always positive. But we're going to go ahead and we're going to write down the definition first of the ratio test so that we can get you used to it. My advice is to write the definition every time you use it. And by the time you're done with this homework set, you'll have it memorized, all right? I don't recommend sitting down and actively memorizing. I recommend writing over and over and over again and sort of memorizing by osmosis. So our definition is that rho is the limit as n goes to infinity of the absolute value, we're testing absolute convergence, of an plus 1 over an. Now, we have to use the formula to prove this for all successive terms. So we're going to have the limit as n goes to infinity, my n's are starting to look like h's, of the absolute value of, we're going to replace n with n plus 1. So we have 4 over n plus 1 over n plus 1 quantity squared. Now, make sure when you're writing a sub n plus 1 that you take each of the n's, put them in parentheses, and replace them with n plus 1. So it's not n squared plus 1, it's n plus 1, the quantity squared. And it's 4 to the power n plus 1. A sub n is always going to match the original summand. So we have 4 to the n over n squared. Now, we happen to know that, in fact, because of the nature of the summand, what's right here after the sigma, that 4 to the n is always strictly positive and n squared is strictly positive. So we know that they're always positive. So we can now drop the absolute values. But again, they are there from the beginning because we're testing absolute convergence. Now, to deal with the complex fraction, you're going to take the first fraction and multiply by the reciprocal of the denominator fraction. So we basically end up with 4 to the n plus 1 over n plus 1 quantity squared times n squared over 4 to the n. That's usually the easiest way for students to work with the ratio test in simplifying the complex fraction. So again, the denominator of the denominator, the bottom of the bottom, becomes on top, and the numerator of the numerator, the top of the top, is still on top. And everything that was in between, sandwiched in between those, stays in the denominator. Now, I cannot reduce the n squared over the n plus 1 quantity squared because the bases do not match. The bases don't match, we're stuck, all right? But I do have 4 to the n plus 1, and I have 4 to the n. I can strip one of the powers of 4 away, and I can rewrite this in a slightly different form. I can write this as 4 times 4 to the n. Isn't that the same thing as 4 to the n plus 1? The bases are both 4. I add the powers. The power's not written here, but it's understood to be 1. And then I would get 4 to the n plus 1. Well, the advantage is now this 4 to the n matches that 4 to the n, so I can reduce. So I've rewritten that, and the 4 to the n's cancel. And now I've got the limit as n goes to infinity of 4n squared over n plus 1 quantity squared. Now the 4, as we know, is a constant factor. It can be pulled out of the limit, so it's not going to affect things. And I've got n squared and I've got n plus 1 squared. So I could either multiply out the denominator, which is not too bad if it's squared, but gosh, if it's to the 5th power, I don't want to go there. But notice these have the same power. So one thing I can do is I can pull the 4 to the front, and I can rewrite the limit with both the n and the n plus 1 in parentheses and the 2 on the outside. Because again, the rule is If you have factors being divided and a power outside, then the power applies to each one of them individually, which would give me back the original. Now, what's the advantage of that? Well, I happen to know that I can pull the limit inside of a power or a radical. So now I can pull the limit inside that power, and I can take the limit as n goes to infinity of n over n plus 1, and then I can square the result. Now, n over n plus 1, they're both linear expressions, so this gives me the form of infinity over infinity. And of course, you can apply L'Hopital's rule. So let me see if I have a little more space here. So if I apply L'Hopital's rule, I get the 4 on the outside. I get the limit as n goes to infinity again, and I have 1 over 1 quantity squared. Well, the limit of 1 is 1, and then I square it, so I get 1 squared, which is still 1, then I multiply it by 4, so I get that rho is equal to 4, which is bigger than 1. Therefore, the series n equal 1 to infinity of 4 to the n over n squared diverges by the ratio test. Now, I said we were doing the wrong thing first, that really we should have done something else first. What is always supposed to be step 1? The easiest of all of the tests that we've studied, it's the divergence test. If the limit of the sequence of terms does not go to 0, it is not possible for the sequence of partial sums to converge to a finite value. So if the limit of the sequence doesn't go to 0, I could have stopped right there. If I look at this sequence, remember what we talked about earlier with the relative growth theorem. This is an exponential divided by an algebraic. I know the exponential grows on an order of magnitude larger than the algebraic. And again, you can use L'Hopital's rule to prove it. But basically, the divergence test would have told me from the beginning that it wasn't possible. The limit as n goes to infinity of 4 to the n divided by n squared. I have infinity over infinity. I can either use the relative growth theorem and just claim from the beginning that 4 to the n overpowers an algebraic and pulls it to infinity, or I could apply L'Hopital's rule twice. I'm still going to get the same result. Eventually, you're going to get that this goes to infinity. Well, because the sequence does not go to 0, it must diverge by the divergence test. Now, I told you not to click on the link at the beginning because I didn't want you to know ahead of time. And it's pretty obvious when you plot this in the sequence of partial sums that this isn't going to work, right? I mean, this is the sequence of partial sums. I've computed, I think, up to 30 of them over here, but I can't even get more than 5 on the picture. Remember that the sequence is plotted in orange, and you can see that the sequence of terms is not going to 0. So the sequence is not going to 0, and the sequence of partial sums, the sum of the terms, a finite number of terms, is plotted here in black, and it's also blowing up to infinity, which is not a proof. You cannot use the plotter as a proof, because who knows what happens way out there. Maybe it all comes back down towards 0 and approaches some value. But it does at least give an indication of what you might expect. And in this case, looking at this picture, I would say, whoa, I don't think the sequence of terms goes to 0. I'm going to check the divergence test. Or you could, in this case, check the ratio test first, and the ratio test is going to give you the same result. It diverges. Okay, let's go back to our notes, and let's take a look now at the second one. Again, don't click on the link because I don't want you to know yet which way it goes. But sometimes the divergence test can be a little harder to apply because maybe you're not as comfortable with taking limits of more complicated expressions. When we're looking at this one, there are some things that we can do to simplify the summand. So we have n times the quantity 1/2 to the n. So 1/2 to the n is an exponential function. Remember that n is considered finite. We are going to be doing the limit as n goes to infinity, but from now, n is finite. And so we're actually able to rewrite the series in a different format where we have n times, well, 1 to the n would be 1, and this becomes 2 to the n. So I could write it as n times 1/2 to the n. But then if I wanted, I could slide them together into the same ratio. And this would give me the sum from n equals 0 to infinity of n over 2 to the n power. Now, if I'm looking at that with the divergence test, so I'm going to apply the divergence test first, I can either use the relative growth theorem or I can use L'Hopital's rule. But the limit of the sequence is n goes to infinity of n over 2 to the n. The numerator's algebraic, n to the first. The denominator's exponential. Exponentials overpower all algebraic functions, but the exponential's in the denominator. So this goes to infinity so much faster, it's like the numerator's a constant, which is going to drive it down to 0. But again, you can also prove it. Since it does have form infinity over infinity, you can prove it with L'Hopital's rule, which would just give you the limit as n goes to infinity of 1 over 2 to the n again times the natural log of 2, which of course goes to 0. So we know that the divergence test is inconclusive. It's possible. So now we want to determine with the ratio test. And remember, the ratio test gives us the strongest possible convergence. It gives us absolute convergence if it converges. So now we want to apply the ratio test. So we're looking for rho, and rho is going to be the limit as n goes to infinity of the absolute value of 8n plus 1 divided by a sub n. Now we have the limit as n goes to infinity, big absolute values. And I'm going to use this expression for it over here, n over 2 to the n, since it's simpler. So I replace the n with n plus 1 in the numerator expression. So I get 2 to the n plus 1, all divided by n over 2 to the n. Now, it turns out that these are, in fact, strictly positive. N starts at 0, so it's, well, not strictly positive then, at least not negative. And 1 over 2 to the n is, of course, exponential. In fact, it's decreasing, but it never hits 0. So we know that they're non-negative, so we could drop the absolute values, but they were there in the beginning. We are testing absolute convergence. So then we're going to take the denominator fraction and take its reciprocal and multiply the numerator fraction by the reciprocal of the denominator. So the bottom of the bottom goes to the top, and everything sandwiched in between goes to the denominator. Now, again, I can't cancel an n plus 1 and an n because of the plus 1. So it's considered a factor group, n plus 1. The only thing that will cancel n plus 1 is another n plus 1. I've got 2 to the n, and I've got 2 to the n plus 1, but I can do the same thing I did last time, and I can represent this 2 to the n plus 1 as 2 times 2 to the n. Again, the power on the first 2 is 1, and when the bases are the same, you add the exponents. 1 plus n would give me n plus 1 again. But now I've got 2 times 2 to the n, so the 2 to the n's would cancel. Now let's go ahead and rewrite what we have for rho. Rho is now, well, the 2 that's in the denominator becomes a constant, so we can pull it out. We have 1/2 the limit as n goes to infinity of n plus 1, the factor group, over n. Well, we've already done this one. We've done this one a couple of times. We did it in the previous problem. We know that if we apply L'Hopital's rule, it has form infinity over infinity. If we apply L'Hopital's rule, we get 1 over 1. So the limit is 1. And then we get 1/2 times 1, which gives us 1/2. So the value of rho this time is less than 1. And because it's less than 1, then we can say, therefore, by the ratio test, the series from n equals 0 to infinity of n times 1/2 to the n converges absolutely. And again, absolute convergence means that even if we were to rearrange the terms of that series in such a way that they looked different, looked like it led to a different series, it would in fact converge to the same finite real value, right? So we have absolute convergence on this particular problem, which is super, super nice, right? Now let's take a look at what we have up here for the sequence of partial sums plotter and the sequence plotter. So this is the one we just looked at, n times 1/2 to the n. And you can see the orange dots are the sequence, and they're very rapidly dropping towards 0, which is what we saw with the divergence test. And you can see that the sequence of partial sums is coming up, but then it looks like it's hovering near 2. Now, I can't say that it is 2, because it could be ever so microscopically above 2 or below 2. But it doesn't look like the sequence of partial sums is going to infinity or negative infinity. So it looks to me like it does probably converge, and that is what we found with the ratio test. So the sequence of partial sums plotter does give me a good feel for what to expect, but it is not a proof because it's only giving you a certain number of values. You cannot use that as a proof, right? Graphs never prove anything because you're only looking at a certain number of points. You're not looking at all possible points. So we want to do the ratio test on this one. This one, we're going to do the divergence test as well, but the divergence test on this one is, well, it's far more difficult because of the factorials. We have to use this idea of the factorial being growing faster than exponentials. So at first we might think, well, gosh, I've got a factorial here and I've got an exponential here, but I know factorials grow faster than exponentials. You might at first expect that it might go to infinity, but you also have a factorial in the denominator. So we're going to use that skill of stripping out the first number of terms of the larger factorial to get it to match the smaller one. So we're going to apply the divergence test first. So we're taking the limit as n goes to infinity of the sequence, which is n plus 4 quantity factorial over 4 factorial times n factorial times 4 to the n. Now 4 factorial is 4 times 3 times 2 times 1, which is 24. So we might as well go ahead and write that as 24. Now that gives me a 1 over 24th, which I can pull out, right? So the limit will not depend on a constant. It only depends on anything with n in it. So now I want to take this n plus 4 factorial and break it down until it matches n factorial. So, oh gosh, I don't know if I have enough room. Let's see if I do. N plus 4, what's in front of it? N plus 3, what's in front of that? N plus 2, what's in front of that? N plus 1, what's in front of that? N. Now it matches the one in the denominator. So I stop when I reach the one that matches the denominator, and then I need the factorial because it's got to go all the way down to 1. And then in the denominator, I have n factorial and 4 to the n. And these, of course, are multiplied together. So now I've got an n factorial in the numerator and an n factorial in the denominator, and they will, in fact, cancel one another out. So my limit for the divergence test becomes 1 over 24 times the limit as n goes to infinity of n plus 4 times n plus 3 times n plus 2 times n plus 1, which of course, if I multiplied it out, would be a 4th degree polynomial in n. So it would be n to the 4, something n to the 4th plus something n cubed plus something n squared plus something n plus a constant, all divided by 4 to the n. Now, if you want to use L'Hopital's rule, you have to multiply this out. There's no other way to proceed. If, on the other hand, you want to claim the relative growth theorem, you're essentially done because this is polynomial. So a polynomial is algebraic, and algebraics grow on an order of magnitude slower than any exponential. So the exponential goes to infinity so much faster that it drives the entire ratio down to 0. So we get that this is equal to 1/24 times 0, or 0, by the relative growth theorem. Now, I don't know whether or not your professor, if you're in a different class, will allow you to use the relative growth theorem. So you'll have to check with them first and see if they'll allow you to claim that, or if they'll expect you to multiply this out and apply L'Hopital's rule 4 times to reduce the degree to the constant, and then have a constant over something that's still an exponential. And then, of course, it does go to 0, right? What does this tell us? Well, the divergence test is inconclusive, which means it's possible that the infinite series has a finite convergent value, that the sequence of partial sums approaches a finite value. Not guaranteed, just possible. So now we're going to use the ratio test to determine whether or not that happens. We're going to use the ratio test now. So we're looking for rho. And again, we're going to write the definition for the ratio test. N goes to infinity, absolute value of a sub n plus 1 over a sub n, both coming from the sequence, which is the sum end of the series. So now I'm going to replace all n's in the sum end with n plus 1. Now you've got to be very careful here. And my advice is to create a really large absolute value and not to crowd up your work. Don't use lined paper. It slows you down and creates more errors, about 10% more errors on average. So it's neuroscience. It's not rocket science, it's neuroscience. You have only so much working memory. And if your working memory is having to tell your brain to keep ignoring the lines, that's distracting your brain and using up some of your computing power that you could be using to focus on the mathematics. So stop using lined paper, use blank paper. So now I'm going to replace n with n plus 1 plus 4 factorial. Notice that I took out the n that was here and replaced it with n plus 1. Then I have 4 factorial in the denominator. I cannot take that out yet. I know some students are like, but that's a constant. Why can't I pull it out of the sum? Well, the infinite series, we don't know if it converges. You're only allowed to take the constant out if you know it converges, but I don't know it converges, so I can't take that out. So then I replace n with n plus 1, and the factorial goes on the outside. And then I have 4 to the n plus 1 power. That is the primary numerator. So I'm going to draw a longer division bar to mark the denominator. And then a sub n is the sum end as it originally appeared. So it's going to be n plus 4 quantity factorial over 4 factorial, n factorial, 4 to the n. Now, the next thing we want to do, of course, is simplify that complex expression. We want to think about, oops, and I forgot to write my limit there, as n goes to infinity. We want to think about whether or not those absolute values are important. And because our n was starting at 0, we know that they're not negative to start with. So 4 factorial is always going to be positive, n factorial is going to be positive, and 4 to the n, the exponential, is always positive. So n plus 4 factorial would be, they're all positive. So I can drop the absolute values. They were there in the original. We are testing absolute convergence. So now I've got rho is equal to the limit as n goes to infinity. And I've got, well, n plus 1 plus 4 gives me n plus 5 factorial over 4 factorial, n plus 1 factorial, 4 to the n plus 1 power times, take the reciprocal of the denominator, 4 factorial, n factorial, 4 to the n divided by n plus 4 factorial. Now let's go ahead and cancel whatever we think we can cancel. And then we're going to expand the larger factorials so that we can get some cancellation with the next largest one in the opposite position. So n plus 5 factorial is the largest. It's in the numerator, and n plus 4 factorial is in the denominator. It's the next largest. So I'm going to rewrite n plus 5 factorial. I'm going to back it down 1. So this is going to be n plus 5. So I'm stripping out the first one. And then what's right in front of that is n plus 5 minus 1, or n plus 4 factorial. So I've rewritten my n plus 5 factorial. So make sure you mark through it so you don't use them both. And now I've got an n plus 4 factorial in the numerator and an n plus 4 factorial in the denominator. So those will cancel. What else cancels? Well, I've got a 4 factorial in the numerator and a 4 factorial in the denominator. So those cancel. Now I've got an n factorial and an n plus 1 factorial. I know I can rewrite the n plus 1 factorial. It's here in the denominator, but I can take this one and I can rewrite this as n plus 1, stripping out the first term, times n factorial. That marks through that one. And that means I can cancel the n factorials. All right, now that's probably enough cancellation for this pass. Let's go ahead and clean it up and see what's left. So we have the limit as n goes to infinity. I still have an n plus 5 factor in the numerator. I have a 4 to the nth power factor in the numerator. I have a 4 to the n plus 1 factor in the denominator. And I have an n plus 1 factor in the denominator. Let's see if we've got all of those taken care of. Did we get rid of everything else? So I think I've got everything. N plus 5, that canceled, that canceled, that canceled. 4 to the n, that canceled, that's still there, that canceled, that's still there, that canceled. Okay, so I've got everything. Well, now I can see that I've got powers of 4. I have n on top and n plus 1 on the bottom. So you know you're going to be able to cancel. Some students like to go ahead and write it out. It's not a bad idea. Write this as 4 times 4 to the n. Then the 4 to the n's cancel. So you've got a 1/4 that you can factor out of the limit. So we're still looking for rho. So this is going to be 1/4 the limit as n goes to infinity of n plus 5, the factor group, divided by n plus 1. Now they're both linear, so they're both lines. Basically, one goes through a y-intercept of 5, the other one through 1. But they're linear, which means that they go to infinity. As n goes to infinity, the y value goes to infinity. So we have form infinity over infinity. So we can apply L'Hopital's rule. And this gives us 1/4 the limit as n goes to infinity of 1/1, which gives us 1/4. Now 1/4 is the value of rho, and that's less than 1. And remember, it has to be between closed 0 and open 1. If we get a 1, it's inconclusive. We have to use another test, right? So then we can make our conclusion on this particular problem, and we can say, therefore, colon followed by a period, by the ratio test, this series from n equals 0 to infinity of n plus 4 factorial over 4 factorial n factorial 4 to the n converges absolutely. So any rearrangement of terms will still produce the same finite real value. But again, we don't know what it is. We haven't determined what it is, all right? So we would have to take a certain number of terms to approximate it. The ratio test does not give you a bound, an upper bound or a lower bound on the remainder. The only 2 tests that we've studied that do that so far are the integral test and the alternating series test. All right. And so now we've reached the conclusion. Let's go ahead and look at the sequence of partial sums plotter. and the sequence plotter. And we can see here on this particular one, the orange dots represent the sequence, the list of numbers, all right? And they're clearly dropping to 0 pretty rapidly. And then the black dots represent the partial sum. So this is S1, this is S2, so the sum of the first 2 orange dots. S3, sum of the first 3 orange dots, S4, S5. And it does look as though the sequence of partial sums is approaching some finite value. It's definitely not going to infinity or negative infinity. So this gives us confidence that we've done the work correctly and we found the right result. Okay, let's take a look at another example. This one is n factorial over 10 to the n over 3 to the n. So again, we're going to do this wrong first, and we're going to go ahead and look at the ratio test first, and then we'll look at the divergence test, and we're going to see what happens. Or I guess we should do the divergence test first. Let's go ahead and look at the divergence test. All right, so when we're looking at this one right here, use the ratio test to determine whether or not it converges. If we look at the divergence test, what is this giving us? Well, this expression, this summand, is actually a little bit confusing. I've got both 10 raised to the n and 3 raised to the n. So the question is, could you write that slightly differently? And the answer is, well, yes, I could. I could write this as the sum from n equal 1 to infinity of n factorial times 10 thirds to the nth power. Now, 10 thirds is greater than 1, which means it's an exponential growth equation going like this. Well, then I suspect that by the divergence test, this thing is not going to go to 0, that the sequence itself, the terms in the sequence, if we write them out, I think they're going to blow up to infinity. So I wouldn't even need the ratio test. The divergence test alone is going to tell me it's not possible for the sequence of partial sums to approach a finite value. So if I do the divergence test and I take the limit as n goes to infinity of n factorial times 10 thirds to the n, remember that limits, we can actually split the limit between products. It's the only thing that we can split between products is the limit. And I get the product of these two limits. Well, I know what n factorial goes to. It grows incredibly fast. It goes to infinity. So this is giving me infinity times, well, infinity, which is infinity, and it is not 0. So this one, in fact, diverges by the divergence test. If you had not done the divergence test, would the ratio test have told you that it diverges? Well, let's check it out and see. Let's go ahead and apply the ratio test. We already know it diverges, but let's try the ratio test. So we have rho equals the limit as n goes to infinity. We want to know how accurate the ratio test is. Would it have given us the correct result? And as we're going to see, the answer is yes, it would have given us the correct result. So now we're going to use this particular form right here because it's a little bit simpler. You could have used the original. It's okay if you use the original. So we have the limit as n goes to infinity of a very large absolute value. And again, in this case, the summand is strictly positive. So we can ignore the absolute values, but they need to be there at the beginning. We are testing absolute convergence. So we replace n with n plus 1 quantity factorial times. And I think, well, let's go ahead and use the original. This would be 10 to the n plus 1 divided by 3 to the n plus 1, all divided by n factorial 10 to the n over 3 to the n, right? And then we need to deal with the complex fraction. So we multiply by the reciprocal of the denominator fraction. And this is going to give me n plus 1 factorial. Now I can see I've got an n factorial. So I'm going to go ahead and expand or strip out the first term from n plus 1 factorial and write it as n plus 1 times n factorial. And I'm going to take the 10 to the n plus 1 because I see that 10 to the n. I'm going to write that as 10 times 10 to the n. And I'm going to do the same thing for the 3 to the n plus 1. I'm going to write it as 3 times 3 to the n times 3 to the n over n factorial 10 to the n, right? So I've got my different expressions here, and maybe I can create a little more space between those two so it's not quite so cluttered. Well, now I can cancel the n factorials. I can cancel the 10 to the n's and the 3 to the n's. So let's go ahead and cancel n factorial, 10 to the n, and 3 to the n. Now, what does this give us that we have left inside the limit? I've got a 1/3, which is a constant, so it can be brought outside the limit. It doesn't depend on n. And then I have the limit as n goes to infinity. Oh, I've got a 10 as well in the numerator, so I get 10/3 on the outside. And then I have n plus 1 left in the numerator, and that's it. I have n plus 1. Well, what is the limit of n plus 1? It's infinity. So infinity times 10/3 is still infinity. So again, we see that because rho ends up being infinity, it diverges by the ratio test as well. So even if you forget to do the divergence test first, you're going to get the same result with the ratio test. So if you find the ratio test easier than applying the divergence test, depending on what the sum end is, you're still going to catch that it diverges. Let's take a look at what this one looks like on the sequence of partial sums plotter. So when we're looking at this, we can see very quickly it's not going to converge because the orange dots, there's one underneath the black dot. They're hard to see, but they're here, here, and here. They're going to infinity. The sequence of partial sums, or the sequence of terms, does not go to 0. And then the black dots is the sequence of partial sums, the sum of the orange dots, and it's also going towards infinity. So we know that the infinite series is not going to converge. Okay, we have 2 more examples to work. Let's take a look at this one. Now this one is a little bit of an interesting one. This is the first time we've seen the tower function. We have n to the n power, which is a tower function, which grows the fastest of all possible functions. So if we apply the divergence test first, by looking at the limit of the sequence of terms, the limit as n goes to infinity of n factorial over n to the n. Now, there's no way to take the derivative of n factorial, and there's no way to take the derivative of n to the n either. There's no derivative defined for either type of function, at least not that I'm aware of for n to the n. There's not for n factorial. You can apply L'Hopital's rule, but you can apply the relative growth theorem. Factorials, though they grow incredibly fast, don't grow as fast as tower functions. So the tower function grows in an order of magnitude larger, overpowers the factorial, and drives it down towards 0. And this time we are going to go ahead and look first at the sequence of partial sums plotter. So we're going to take a look at that, just to reassure ourselves that yes, in fact, the divergence test is inconclusive. We can see the orange dots here going towards 0. And we can also see the sequence of partial sums. And while it looks like there could be a little bit, it's hard to tell if there's any oscillation or not, but it looks like there might be. It clearly isn't going to infinity or negative infinity. So it does look as though the sequence of partial sums converges to some finite value. But again, the plotter cannot give you a proof because there could be some oscillation where it's going back and forth between 2 very small numbers. And if you don't blow it up large enough, you won't be able to see that. So it gives us an indication, but it's not a proof. For a proof, we need the ratio test. So now we're going to do the ratio test. So we're looking for rho, which is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. This time I want you to pause the video, go ahead and see if you can simplify this one and get the result on your own, then turn the video back on and compare your answer to mine. I fully expect that you got stuck somewhere along the way. So let's go ahead and proceed partway through, then we'll pause the video again to see if you can work your way through the rest of it. So we got this far. We got to the a sub n plus 1 over a sub n. Remember to replace all n's in the original summand with n plus 1 in parentheses. So that gives us n plus 1 factorial over quantity n plus 1 to the n plus 1 power divided by n factorial over n to the nth. Now I knew, because I was going to cancel like things, that I wanted to strip out the first term of n plus 1 quantity factorial. So I wrote it as n plus 1 times n factorial. I did a similar thing to the power in the denominator, the tower function. I took n plus 1 to the n plus 1 power, and I wrote that as n plus 1 to the first times n plus 1 to the nth. Now again, this is just using the rules for exponents. When the bases are the same, you add the power, so you get n plus 1, which is what we originally had. Then I multiply by the reciprocal of the denominator fraction. Now this gives me n factorials, which are common. So I can go ahead and cancel the n factorials. And notice this time, unusually, we didn't have this happen before, but we have an n plus 1 to the first power canceling an n plus 1 to the first power. So these guys actually cancel one another and they're gone. Now we cannot reduce this right here because the bases are different, and the exponent rules only apply when the bases are the same. But this does give us the limit as n goes to infinity of n to the nth over n plus 1 to the nth. So they're both raised to the nth power, so I can combine them into one ratio, n over n plus 1, and raise that to the nth power. Now it is tempting to want to bring the limit on the inside, but you really can't, because this power is not a constant. It depends on n. The limit depends on n. So you're not allowed to pull the limit inside the power. Instead, what you do is an algebraic trick. You multiply by 1 over n over 1 over n. It's actually not necessary that you do that. You could have left it n over n plus 1. You could have left it in this form here, but I kind of like doing it the other way. I'll leave you to do it either way. All right. So if you want to follow along, you could have left it like this, because n over n plus 1, as n goes to infinity, you know that approaches 1. So we have the form 1 to the infinity right here. So we could have stopped and we could have applied the next steps to that expression right there. All right. Or you can do this algebraic trick, which makes it more obvious. The numerator becomes 1, the denominator becomes 1 plus 1 over n. And then you know for sure that what's in the parentheses is approaching the value of 1. And so you have the form 1 to the infinity, which, as we know, is an indeterminate form and requires L'Hopital's rule. But because it's a power form of the indeterminates, we have to take the logarithm of the expression, and to undo that, we have to apply the 1-to-1 inverse operation, which is to exponentiate it. So we take e to the natural log power, and then we pull the natural log on the inside. So we're taking this like here. Now, we could also have done it in this form right here. So you could have come down. Let's see if I have space. Looks like I have a little bit of space. So you could have come and applied it there. So we have the limit as n goes to infinity of, I believe it was n over n plus 1 to the n, which we know has the form 1 to the infinity. So you could have exponentiated, and you have the limit, which you can pull inside the power because the base e does not depend on n, it's constant. And then we have the natural log of n over n plus 1 to the nth power, right? And then, of course, you could pull the power to the front. You can do that in either form. So if you pull the power to the front, then you have e limit, n is still going to infinity, and you have n times the natural log of n over n plus 1. Well, n is going to infinity, so this has the form of infinity times, well, what is the natural log of n over n plus 1? Well, as n goes to infinity, n over n plus 1 approaches 1, and the natural log of 1 is 0. So we've reduced it from being a power form, 1 to the infinity, to be an arithmetic form, infinity times 0. But that's not good enough. We got to have a basic form, 0 over 0 or infinity over infinity. Then we can do L'Hopital's rule. So I never move natural log. Natural log always stays put. So I'm going to move the factor n by dividing by the reciprocal. So that gives me e, limit as n goes to infinity still. The stuff is just hanging out. And I have, well, let me create some more space here. Move that down a little bit. All right. Right? So now I've got the natural log of n over n plus 1, and I'm going to divide by 1 over n, right? So I've moved the factor that was giving me the infinity, and infinity times 0, and I've moved it, and I'm dividing by the reciprocal. And we know the denominator is really the numerator, so it's equivalent. But now when I look at this, I again have natural log of 1, which goes to 0. So this has form 0 in the numerator. But 1 divided by something going to infinity also has form 0. So now I have the form of 0 over 0. That's one of the basic forms of the indeterminate forms. And so I'm allowed to do L'Hopital's rule. So now I do L'Hopital's rule, which says that the limit of this ratio is equal to the limit of the ratios of the derivative of the numerator over the derivative of the denominator. Now that only applies if they're continuous functions, but as n goes to infinity, they are continuous and differentiable functions. So I have e to the limit n goes to infinity. Now, what's the derivative of natural log? 1 over u times the derivative of u. Now, 1 over a fraction is just the reciprocal of the fraction. So you can rewrite this instead as n plus 1 over n. Then you need to multiply by the derivative of n over n plus 1. So I need to take the derivative with respect to n of n over n plus 1. I don't want to do too much at once, so I'll leave that like that. Now, I also need to take the derivative of the denominator, but I'm going to think of the denominator as n to the negative 1. So that gives me negative 1 n to the negative 2, which of course would give me negative 1 over n squared. Now, when I'm looking at this, I need to go ahead and complete L'Hopital's rule by finishing out the derivative of that quotient there. So now I'm going to take the derivative of the ratio. So I've got e limit, n is still approaching infinity. I can't do the limit yet. So I've got n plus 1 over n. I've got now the derivative. So I'm going to have the denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator, which is 1, all over the denominator squared over this negative 1 over n squared, right? And you can keep going like this. You may want to pause the video or you may want to speed it up a little bit. So what do we have from here? Well, I've got an n plus 1 on top and 2 n plus 1s on bottom. So one of these cancels one of these, and I'm left with 1 in the denominator. So I have e limit n goes to infinity. What happened to my limit? And then I've got in the numerator, I've got the n plus 1 canceled. So I have an n plus 1. And then I need to look at what happens with this part right here. Well, I have n plus 1 minus n, which just becomes 1 because the n's will cancel. So I get a 1. And then I can multiply this by the reciprocal of the denominator, which is negative n squared over 1. So one of the n's will cancel. And what do I get from this value? Well, keep going. This is a really long, difficult problem. And what I end up with is negative n over n plus 1. But again, this has the form of infinity over infinity. So I can apply L'Hopital's rule again. And this gives me e to the limit as n goes to infinity of -1 over 1, which gives me e to the -1. E to the -1 is 1 divided by e is about 2.718281828.459, blah, blah, blah. And so I know that this value is less than 1. Therefore, by the ratio test, the original series must converge absolutely. Now, could you have done it in that other form that I had up above? Yes, in fact, you can. It's just about as difficult. It's not really any easier. If you had applied that trick, so it became 1 over 1 plus 1 over n, then you do the same thing. You exponentiate and take the natural log of the expression. That pulls the n to the front, which gives you the arithmetic form infinity times 0. Then you divide by the reciprocal of n, which is 1 over n. And then you have to take the derivative of the numerator and derivative of the denominator. You are again, of course, here doing L'Hopital's rule, so I should have that marked. So you have 1 over u, 1 over that fraction, which puts this in the denominator of the denominator, so it jumps to the numerator. And then we have the derivative of what was u, but I wrote u as 1 plus 1 over n to the -1. So that gives me negative this to the -2, or -1 over that squared. So one of these cancels one of those. And then I have to multiply by the derivative of the inside, which gives me a -1 over n squared. And then I divide by, of course, the derivative of the denominator, which was 1 over n. So its derivative is -1 over n squared. Notice that we have a -1 over n squared in both positions, so they cancel. That cancels one of these, and I end up with -1 divided by 1 over 1 plus n, which of course then has the same limit value of -1, which gives us 1 over e, and we have the same conclusion. By the ratio test, this infinite series must converge absolutely. So any rearrangement of the terms is going to cause the sequence of partial sums to again add up to exactly the same value. Now, when we were looking at this one, I can't remember if we actually looked at this or not. It looks like we did. So we've already looked at that one. Is that correct? In Factorial, yes, we did. So we've already looked at that. So let's go ahead and proceed to the last example, which is example number 6. This one is more difficult. This one is going to require us to use both the comparison test and the ratio test. So it's a combination of two tests to show that the series actually converges absolutely. So when we're looking at this one, what might we compare it to? Well, again, we focus on the denominator, where you have 2 plus n times 3 to the n. It looks to me, because the denominator has a 2 plus, making the denominator larger, which makes the entire ratio smaller, that I could compare it to something bigger, which would be 4 over n times 3 to the n. So I'm comparing it to something that's slightly larger in value. The denominator is smaller, so it's going to be larger. So again, I can show that n, well, let's see, what would I start with? 0 is less than 2. So 0 plus n times 3 to the n has to be less than 2 plus n times 3 to the n. I'm starting with something I know is true. I'm trying to build that comparison series. And then I know that because n is greater than or equal to 1, so n times 3 to the n is strictly greater than 0, and 2 plus n times 3 to the n is strictly greater than 0, because n is strictly greater than or equal to 1. So I know both of those are positive, so I can divide both sides of the inequality by each one, and this lets me write 1 over 2 plus n times 3 to the n must be less than 1 over n times 3 to the n. And then I can multiply both sides by a positive 4, which will not reverse the sense of the inequality. And so this then leads to the following, that 4 over 2 plus n times 3 to the n must be less than 4 over n times 3 to the n. So this becomes my comparison series. So I want to look at that series instead. So I know that this original series is going to be less than equal to a series with this as the summand. That's the comparison test. The unknown less than equal to something else. Now, this is only going to work if I can prove that one actually converges. So I need to show that the comparison series which is the sum from n equal 1 to infinity of 4 over n times 3 to the n converges. In fact, I'd like to show it converges absolutely, right? So how do I show it converges? Well, first I should check the divergence test just to make sure that the limit of the sequence does go to 0. So I'm going to take the limit as n goes to infinity of the sequence, which is 4 over n times 3 to the n, which very clearly goes to 0. And so the divergence test is inconclusive. Remember, divergence test only tells you, hey, this guy diverges because the sequence doesn't go to 0. If it does go to 0, it doesn't tell you anything. So it's still possible. So now I'm going to use the ratio test. Now, why would I think to use the ratio test? Well, I've got an algebraic function n multiplied by an exponential 3 to the n, so the ratio test is a good choice. So when I'm looking at this particular one, integrating this would be difficult, right? Very, very difficult. In fact, we may not be able to integrate it directly. So what we're going to do is we're going to apply the ratio test. We're going to look at rho, which is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So go ahead and pause the video, work this one out. You'll find this one's not quite so difficult as the last one. And then turn the video back on and compare your answer to mine. Okay, how did you do? Remember, we're trying to compare this to the series of 4 over n, 3 to the n. And we saw that it is an inconclusive result with the divergence test, so it's possible that it converges. And we apply the ratio test. Remember to replace the n's in the summand with parentheses n plus 1. So we have 4 divided by n plus 1, the quantity, times 3 to the n plus 1, divided by the original summand. Now, these are all strictly positive because n is greater than or equal to 1. So we can drop the absolute value, but they were there. So we are testing absolute convergence. Then I take the numerator fraction multiplied by the reciprocal of the denominator. And you'll notice that I went ahead and I expanded 3 to the n plus 1 power as 3 times 3 to the n, because I knew I was going to want to cancel some things. So the 4's definitely cancel, and the 3 to the n's definitely cancel. And that then tells me that I've got a 1/3 from the 3 in the first fraction's denominator that I can pull out of the limit. The limit does not depend on the constant. And that will leave me with n over n plus 1 inside the limit. Now, we've done that multiple times today. We know that if we apply L'Hopital's rule, we get the limit of 1 over 1, which is 1, and 1 times 1/3 gives us 1/3. Notice that it was important that we use the comparison series 4 over n times 3 to the n. If I had compared it to 1 over 3 times 3 to the n, the 4's would not have canceled. And if the 4's hadn't canceled, rho would have ended up 4/3, which wouldn't have proved it, right? So I need to make sure that I'm using the right comparison series. So in this case, what I found is that the value of rho is 1/3, which is less than 1, which means, of course, that we do have convergence. So when I'm looking at this one, I've got the ratio test showing that 4 over n times 3 to the n converges absolutely. So that one is okay. And then because that converges absolutely, and because my unknown series is smaller than that known convergent series, then the unknown series must converge by the comparison test. So we're using a combination of both the ratio test and the comparison test to work these out. Now, you do want to be very careful that you're using the right comparison. In this case, the 4 would be there no matter what, because it's a sub n plus 1 over a sub n. But you do want to be careful and make sure that whichever comparison test or series that you use, that you apply it correctly so that you can get convergence, so that you can then use the comparison test. So this is the end of our examples for the ratio test. I think you'll find that the ratio test is actually kind of fun to apply. It's relatively straightforward. It's very calculations based. It does require you to evaluate a limit, so you've got to be very good at limits. We saw how L'Hopital's rule got brought up a lot of times. And in fact, on one of them, we needed to exponentiate and take the natural log of what was inside the limit because we had a power form of the indeterminate form. So again, we see that the ratio test is very versatile and very strong. As long as the terms in the sequence are eventually non-zero, we can apply the ratio test. Now we have one more test to do, and that would be the root test, which will be our final test. And it's actually a very short test and very easy to implement, even easier in some ways than the ratio test. So it's very short. The conclusions, however, match the conclusions for the ratio test, which makes it sort of easy to remember. The two R's have the same conclusions. Again, as long as rho is between closed 0 and open 1, it converges absolutely. If rho is greater than 1 or infinity, it diverges. And if rho equals 1, it's inconclusive. We have to try another test, probably the integral test if the terms are non-negative, or maybe the limit comparison test also if the terms are non-negative. I hope you'll join me for the next video when we discuss the root test.